Hi, everybody. It's Professor Mitchell. We're starting a brand new chapter today, Chapter 10 on infinite sequences and series. This chapter is going to take us pretty close to the end of the semester, believe it or not. I believe it has 10 sections. So let's get started. All right, section 10.1 is about sequences. Most of the rest of the chapter is about series. So we'll start looking at those in the next section. A sequence is a list of numbers, a sub 1, a sub 2, a sub 3, et cetera, with the general term being called a sub n, in a given order. A sub 1, a sub 2, a sub 3, etc. are called the terms of the sequence. More precisely, a sequence is a function whose domain is the set of positive integers. F of 1 equals a sub 1, f of 2 equals a sub 2, etc. Sequences can be described by writing rules that specify their terms, such as a sub n equals the square root of n, b sub n equals negative 1 to the power n plus 1 times 1 over n, or by listing terms. So these are the same sequences that were just defined. So the first bullet here is a sub n equals the square root of n. So the first term is the square root of 1. The second term is the square root of 2, et cetera, et cetera. And then b sub n, the first few terms are 1, negative 1/2, 1/3, negative 1/4, etc. Please take note of the alternating signs in this sequence. This is a pretty common thing. And to make that happen, you put negative 1 to a power. Usually that power will be either n plus 1 or n, depending on whether you want the sequence to start with a positive number or a negative number. So more on that in a little bit. Here are a couple of different ways to graph sequences. I tend to prefer what's here on the right-hand side. It's a little bit more clear to me, but this is a perfectly good way to do it too. So you can either represent them as points on the real line, which is what they're doing on the left side. So in the first picture, we have a sub n equals the square root of n. Here's a sub 1 equals the square root of 1, a sub 2 equals the square root of 2, square root of 3, square root of 4, etc. A sub n equals 1 over n. Here's 1 over 1, 1/2, 1/3, 1/4, 1/5, etc. And then negative 1 to the power n plus 1 times 1 over n. You have 1, and then way over here you have negative 1/2, positive 1/3, negative 1/4, positive 1/5. On the right side, those sequences are being plotted in a plane where on the n axis, you just have what's called the index number, 1, 2, 3, 4, 5. And then the value of the sequence, a sub 1, a sub 2, a sub 3, is what we traditionally think of as the y coordinate. So here's the point 1, 1, 2 comma square root of 2, 3 comma square root of 3, etc. 1 comma 1, 2 comma 1/2, 3 comma 1/3, and finally 1 comma 1, 2 comma negative 1/2, 3 comma 1/3, etc. All right, so we have reached our first example. Just notice that it's in two groups. So in the first batch of examples, we will find the first 4 terms of the sequence. And then in the second batch, we will find a formula for the nth term of the sequence. So let's go over to the tablet. All right, just in case you're not familiar with this notation, this is usually not read a sub n equals 1 over n. All right, sorry, I have to make that joke every time I introduce this notation. This exclamation point means factorial. This is n factorial. You would have seen this if you've taken a statistics class. N factorial is defined as follows. If n is an integer greater than or equal to 1, then n factorial is defined as n times n minus 1 times n minus 2, all the way down to 1. So for example, well, 1 factorial would just be 1. There would only be one factor in that multiplication problem. 2 factorial would be 2 times 1, which is 2. 5 factorial would be 5 times 4 times 3 times 2 times 1, which I believe comes out to 120. All right, and then by definition, a separate part of the definition, 0 factorial is defined to be 1. Okay. So again, just separate part of the definition. This up here does not cover the case where n equals 0. Okay. You're going to be seeing a lot of factorials in this chapter. All right, so very easy to write the first 4 terms of this sequence. Remember, that was what they wanted us to do. So let me make some room to do that. All right, here we go. So a sub 1 would be 1 over 1 factorial, which is just 1. A sub 2 would be 1 over 2 factorial, which is 1/2. A sub 3 would be 1 over 3 factorial, which is 1 over 3 times 2 times 1. So that would be 1/6. And finally, a sub 4 would be 1 over 4 factorial, 4 times 3 times 2 times 1, 1 over 24. So there you have it. That's the first 4 terms of that sequence. All right, next example, a sub n equals 2 to the n minus 1 divided by 2 to the n. So a sub 1 would be 2 to the 1, subtract 1 divided by 2 to the 1. So that would be 1/2. A sub 2 would be 2 squared minus 1 over 2 squared. 2 squared is 4. And then notice that the numerator is always exactly 1 less than the denominator. So that might speed up our work a little bit going forward. 2 to the 3rd power is 8. 1 less than 8 is 7. And finally, 2 to the 4th is 16. 1 less than 16 is 15. And those are the first 4 terms of that sequence. All right, so those problems, that type of problem, find the first however many terms of the sequence, tend to be very easy. What's a little harder is going the other way around. So I give you the first few terms of the sequence and you write a sub n, the general term. All right, so this is all about finding patterns. So let's see what patterns we can find in this list of numbers. So for one thing, what if I pointed out to you that 1 can be written as 1 over 1 squared, and 1/4 can be written as 1 over 2 squared, 1/9 can be written 1 over 3 squared, etc. Okay, so a big part of this general term is going to be 1 over n squared. Okay, so now we just have to talk about how to make the signs alternate. So we need the first term, and as I mentioned before, that's done with -1 to a power. So we just have to decide, should that power be n or should it be n plus 1? Well, in this case, it should be n plus 1. And the reason is when n equals 1, that part of it would come out to -1 squared, which is 1. We want the first term to be positive. The second term would start with -1 to the power 2 plus 1, so -1 cubed, which is -1. Okay, so this, putting this as part of the sequence makes the signs alternate starting with positive. Okay. If we wanted them to start with negative, we would have used -1 to the power n. So that would make it go negative, positive, etc. All right, next example. Letter B, we have -3/2, -1/6. Oh yeah, 1/12, 3/20, 5/30, etc. Okay. I did a double take when I saw two negative signs and then the rest were positive, and then I remembered why. All right. Okay, so again, it's about taking apart the pattern. So let's look at the numerator and the denominator separately. In the numerator, why don't we build in this negative sign? We have -3, -1, 1, 3, 5. Okay. That is what's called an arithmetic sequence. What makes it arithmetic is that the terms are going up by a constant number, in this case 2. Okay. All right, so the way that you make that happen, let's see. So we want the first term to be -3. So we're going to go, let's see. What sometimes helps me do this is by making a chart. So when n is in the Math for Teachers class that I teach, there is actually a formula to do this. I'm not going to bother you with that. I don't want to call this column a sub n because it's not the whole a sub n, so I'm just going to write it here. And let's put the 4 down here. Okay. As I mentioned, they're going up by 2s. So what makes that happen is a +2. So imagine we did, oh wait, no, what makes that happen is 2n. So if this is 2n, it would go 2, 4, 6, 8. Okay. So now what I want you to notice is that all of these terms are exactly 5 bigger than all of these terms. All right, so in order to get the numerator that we want, instead of doing 2n, we will do 2n minus 5. And that'll give us what we want. Okay, so we're halfway there. Excuse me, we want to make the numerator 2n minus 5. All right, and then the denominator, let's talk about the denominator. I'll point out a pattern, an interesting pattern to you about the denominator. So I'm going to write 2 as 1 times 2. I'm going to write 6 as 2 times 3. 12 is 3 times 4. 20 is 4 times 5. See how that works? This is probably another one of those tricks that you just pick up from experience. All right, so the first factor in each of those denominators is the number n, right? First term, second term, third term, fourth term. And then the second factor is just the number that's 1 bigger. So what you can do to get that is do n times n plus 1. All right, and then the last example from this batch, this is a really interesting one, okay? So it goes 0, 1, 1, 2, 2, 3, 3, 4, okay? So it's pretty clear what that pattern is. What's not super clear is how to write a formula that makes that happen. So there are probably a few ways to do this. And in fact, the one that I have in mind may or may not be the same one that your textbook thought of. But here's the way I would do it, okay? So bear with me here for a second. Imagine that underneath these numbers, I put 0.5, 1, 1.5, 2, 2.5, 3, etc. 3.54. Okay. And then imagine I was allowed to round those numbers down. Okay, so here's a function that you hopefully saw in Calc 1. It's called the floor function. And it's written like this. Okay, so the definition of that function, the floor of x, it is the greatest integer that is less than or equal to x, also known as the round down function. Okay, so if I rounded all these numbers down, that would give me what I want, right? 0.5 would round down to 0, 1 would stay at 1, 1.5 would round down to 1, 2 would stay at 2, okay? All right, so now as long as I can figure out how to make 0.5, 1, 1.52, et cetera, we are in business, okay? Well, that is another arithmetic sequence. These terms are going up by a constant 0.5 each time. So I'm going to use a similar trick to what I did to get the numerators in the last problem. I'm going to make a little table. So when n is 1, 2, 3, 4, I'm going to leave that column blank. And to make the numbers go up by 0.5, let me start with 0.5 n. Oh, I think this is going to give us exactly what we want, isn't it? 0.5 times 1 is 0.5, 0.5 times 2 is 1, 0.5 times 3 is 1.5. Excellent. So in this case, we do not have to add or subtract something like we did in the last problem. All right, so we can just say that a sub n is the floor of 0.5 n. Those of you who are computer science majors, the floor function is a very, very, very useful function in computer science. All right, so that's going to do it for that example. Let's go back to the presentation. All right, convergence and divergence. Remember, we started using this terminology in the last section, 8.8. And what that meant in 8.8 roughly was that if the improper integral had a specific value, then we said that the integral converged. And if it did not have a specific value, which usually meant it was infinite, then we said it diverged. All right, and that's roughly what it's going to mean for sequences. There is another way that a sequence can diverge, so we'll talk about that. All right, so look at the picture here. In the representation of a sequence as points in the plane, a sub n, the sequence a sub n approaches L if y equals L is a horizontal asymptote of the sequence of points. Okay. So I'll always remember one of my professors when I was in college described it like this. Imagine that you built a tube around the number L. What it means for the sequence to converge is that no matter how narrow you make that tube, eventually all of the numbers in the sequence will fall within that tube. Okay. So that's what they're talking about by the number epsilon. You might have flashbacks to Calc 1 when I start talking about epsilon. The width of this tube is 2 times epsilon. Okay. So in this case, imagine that epsilon is, I don't know, 0.1. Okay. So it looks like all of the terms of the sequence starting with the 7th term land within this tube when epsilon is equal to 0.1. Now, if I made epsilon smaller, say 0.01, then the terms of the sequence would not fall within the tube starting at n equals 7. Maybe they would start falling within the tube at n equals 50. Okay. But the point is that eventually, starting at some number, all of the terms of the sequence will be inside the tube from that number on. All right, so here is the official definition. I'm not going to do a whole lot with this. The sequence a sub n converges to the number L if, for every positive number epsilon, there corresponds an integer n, big N, such that for all little n, if little n is greater than big N, then the distance between a sub n and L is less than epsilon. Okay. So that's the symbolic way of representing what I was just saying about the tube. No matter how narrow you make that tube, and the narrowness of the tube depends on epsilon, all of the terms of the sequence from some number on, some number is big N, will fall within the tube. And then if no such number L exists, we say that the sequence diverges. If a sub n converges to L, we write limit as n increases without bound of a sub n is equal to L, or simply a sub n approaches L, and we call L the limit of the sequence. All right, so one way in which a sequence can diverge is if the terms are going off towards infinity or negative infinity. So in the top picture here, the sequence diverges to infinity because no matter what number m is chosen, the terms of the sequence after some index n all lie in the yellow band above m. In other words, they're all greater than m. And similarly, the sequence diverges to negative infinity in the bottom picture because all terms after some index n lie below any chosen number little m. Okay. So in other words, your sequence diverges, and we'll stick with diverges to positive infinity, if all of the terms from some point on are greater than, say, 1,000,000 or 1,000,000,000 or 1,000,000,000,000. And the sequence diverges to negative infinity if all of the terms of the sequence from some point on are less than negative 1,000,000 or negative 1,000,000,000. Okay. All right, so that is the official definition of diverges to infinity and diverges to negative infinity. I'll skip reading this to you this time. Okay, now I didn't think about this before. I guess maybe I assumed that they would talk about it, and maybe they will. I just want to make sure. There is one other way in which a sequence can diverge. And I want to show you a picture of that. So it may not be that the sequence is going off to positive infinity or negative infinity. It could just be, I'll give you a real simple example. Let's say that this is the number 2 and this is the number 4. And your sequence just goes 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, et cetera, et cetera. It does that forever. That sequence would also diverge because it's not approaching any one specific number. Okay, so this is another important type of divergence